Okay. It seems like to me that just slipped another slide, but maybe that's where we belong. Let's get the slideshow set up from current slide. Yeah, we talked about the interest thing, right? Yeah, I thought so. All right, before we get started here, it's been so long because we didn't have class at all last week. We just had it 2 weeks ago. So since then, the way we do things here is sometimes a little bizarre. During our in-service meeting at the first of the term, the administrator said, "Oh, there's a new logo, and you got to have the new logo on your syllabi." Okay, so and they actually then later sent an email and said the new blah blah is at the website here, you know, at the L Drive. So I went there, there was nothing there, but I found where the logo was and that kind of stuff, and got that done. Remind me, name? Amber, okay. I know you're in here. There you are. All right. Okay. And so I put in the new logos. They were a pain in the neck to do because they're all three separate. Well, two logos in one. And name, please? Monica. Got it. All right. Okay. So I got those done, and that's probably what you saw 2 weeks ago, or last Thursday, 2 weeks ago. Then, after we had gotten all those set up, they said, "Oh no, you need these extra paragraphs in here too." So we had to go back and change all of our syllabi to match what they wanted. Okay, so the new syllabus. The guts of it, the important stuff, that hasn't changed. You know, what we're doing in the course and stuff. It's just now they've added things on plagiarism and student conduct and I don't know, a whole bunch of stuff. So, but we're required to put it in, so it's in there. So if you want to go and check that out, it's there on Blackboard. Now, all of you were here last time, right? So you all know how to locate things in Blackboard. It's under content. Okay, now I'm trying to remember what I had done as of last time. Also under content is the research paper instructions. We went over those. My locator card, I may have changed that some because I don't remember if I knew the physical science class was being canned completely, and I adjusted some things around lunch and stuff like that. Okay? Then I put all of the PowerPoints that we could possibly do this term. Probably more than we will do this term. So they're out there. I don't know if I had all those done last time. Can I get your name, please?
Jayla.
Huh?
Jayla.
Jayla. Webster? Okay, I thought so. Okay. All right. Anyone else come in since the call roll? Okay. Now, so all the PowerPoints are out there now. I also put all the links to websites that either students have given me or I found that I thought might be helpful, and the link to the YouTube videos. So if any of you missed any of the earlier classes, they're there under the YouTube videos. All that's under content. Okay, any questions before we move on? Okay, last time we were talking about this formula here, I is equal to 1,000 R. Now, remember what that was. If you put $1,000 in the bank and you're earning R% interest, that's the rate, then if that's a yearly rate, then at the end of 1 year, you earn that much interest. Right now, that R is probably like point something, you know, really pathetic. But the interest rates are going up slowly with the Fed increasing things, so that might improve a little bit. That represents a special kind of relation, and we talked about this last time, that matches each item from one set. What were those two sets called? Not A and B, they were called that. What was the name? What were they? The input set was the domain, and the output set was the range. Excellent. Okay, those two sets from one set, the domain, with exactly one item from the different set, the range. Okay, now we talked about this with the bag of chips. Okay, if you have a given interest rate, then you'll earn a certain amount of interest. You don't want one person with this rate earning one interest and another person with the same rate not. That's not fair. Okay, you don't do it. This makes this a function. Such a relation that for each item in the first set, the domain gives you exactly one item in the range. That's then as a function. So here's your definition. A function f from set A to set B, set A being the, and we're going to talk about that, is a relation. Those are relations. Anytime you're comparing two sets, that's a relation. But it's a relation that assigns to each element x in set A exactly one, not more than one, only one element in set B. Okay? Element y in set B. Now, they don't have to be x and y. They don't have to be sets A and B. Whatever they are. The set A is called the domain, or the set of inputs, and of that function f, and the set B is contains the range of the set of outputs, which y'all already remembered. And this definition, middle of page 35. Now, here's another way to express a function. This is called a mapping, is usually what they call this. To help understand that definition, let's look at this function here. Okay? Now, this is degrees Celsius, but it probably maybe a little bit warmer than we are today, but not too much. Okay? This assigns to each time of day from 1 to 6 in the evening, on the hour, we hang a thermometer on the tree out there, and at each hour you record a temperature. Okay? Now, the hour is your input, domain. The temperature at those times, that's the range. Right? How many temperatures can you have at any given hour? You read that thermometer, how many temperatures do you read? One. Okay? That's going to be a function. You can't have two temperatures at the same time, right? Okay? So that's going to be a function. Now, notice at 1 o'clock it was 9 degrees Celsius, which would be, goodness gracious, around 50 maybe, a little bit less than 50. Might be like today, okay? At 2 o'clock you're up to 13 degrees Celsius. I'm not going to figure out all these. At 3 o'clock it had climbed to 15. At 4 o'clock, though, it probably had peaked between 3 and 4, and it dropped back to 15. And then at 5 it had dropped to 12, and at 6 it was down to 10. Okay, now is this legal for the two different times to have the same temperature? Sure, there's no problem there. It's just you can't have two different temperatures for the same time. Can I get name, please? Second. Okay. I'm hard to hear. Okay. Kinesis Mayfield. Is that what you said? Did you say you went by Kayla? Okay. All right. That's what I was thinking. And? Second. Oh, goodness. What a terrible name. Okay. Jasmine, right? Okay. Got it. Okay. So, this is called a mapping. You set the domains here, the elements in the domain, and then you pick out the temperatures there. Now, what's your set A? Set of times, and that would be the set of 1, 2, 3, 4, 5, and 6 o'clock p.m. Set of ranges. Now, you have others you didn't use, but the ones you actually did use were 9, 10, 12, 13, and 15. Okay? There were others in there that you didn't use. Usually you use all your inputs. You may or may not use all your outputs. Okay? Especially negative 73. Not around here you wouldn't ever use. Don't even bother putting it in there. and 105, no, it's not going to be above boiling. Okay, so you wouldn't have that in there either. But that is those are your sets. Any questions on that? Input, output. Now, here's another way you can express a function. You can say it verbally, you can say it, draw it in a mapping, or you can put a set of ordered pairs. The following ordered pairs represent that previous function. At 1 o'clock, it was 9 degrees. At 2 o'clock, it was 13 degrees. 3 o'clock, 15. These were degrees Celsius. 4 o'clock was 15. 5 o'clock was 12. 6 o'clock was 10. Okay? Your name, please? Huh? Okay, my ear is back. Huh? Thomas. Okay. Is that first or last? First, okay. Is that Abrowski? Okay. Is it Bowski or Brown? B-O-W or B-R-O-W? B-O-W. Okay, I spelled it right. And you go by Thomas? Yeah. Okay. All right. And, oh, I think I may know you. Got to find you, though. Chris, right? Okay. All right. Catching up here, folks. Good deal. Okay. So here is another way to express a function. A set of ordered pairs. Okay? Now, this is called the brace. Sometimes offhandedly a curly Q, but it's called the brace. These are parentheses. Now, we'll find out later parentheses are used for all sorts of things. But in this case, they're ordered pairs. Now, ordered pairs, 2 words there, ordered and paired. Both of them important. Got to have 2 to make it a pair, and the order matters. You can't write that as 9-1. That would be at 9 o'clock, it was 1 degree Celsius. No. This was the time so the order matters. Okay? So, and then also you have two entries there. So this is a set of ordered pairs. Now, remember your domain. That question was just a stretch. Okay. Your domain is a set, but that's not a set of ordered pairs. That would be, what would be in your domain? Remember? Say again? Yeah, and what were they for this one? 1, 2, 3, 4, 5, and 6. The first thing in the ordered pair. It's always input, output. That's the order. Your output set?
9, 13, 15.
Okay, you don't have to repeat the 15, 12, and 10. Okay? Do you have to put them in increasing order or decreasing? No, any order is fine, but you don't have to repeat one if it's already set. Okay? So what are some of the characteristics of such a function? From set A, the inputs, to set B, the outputs. Okay? Each element in A must be matched with the element in B. That's what I said before. If your input was those 6 times, you have to match it with the temperature. Okay? Can't have any times that there was no temperature out there, okay? That wouldn't make sense, okay? Now, some elements in B may not be matched with the element in A. We saw that. There were a bunch of temperatures out there that we didn't measure that day, okay? 2 or more elements in A may be matched with the same element in B. That's perfectly fine, okay? But an element in A cannot be, in the domain, cannot be matched with 2 different elements in B. Can't happen. You can't have 2 different temperatures at the same time, okay? So you can have more than 1 times with the same temperature, but you can't have more than 1 temperature at the same time, okay? Does that kind of make sense? That's what a function is. So we've mentioned several ways to represent a function. Here are 4 of the most common. You can say it verbally. The set of temperatures at 6 times of the afternoon, okay, on the hour, okay? That would be to say it verbally. Sentence that describes how the input variable, the time, is related to the output variable, the temperature. You can do it numerically by a table or a list of ordered pairs. Now that list of ordered pairs, and later we'll do this, especially if you're graphing this function, you might want to put the input in the first and the output in the second, have it in a table there. A good old T-table makes it easier to graph. Same ordered pairs, 1 and 9, 2 and 13, same ordered pairs, it's just you do them in tabular form rather than ordered pairs form, okay? So that's numerically in a table or a list of ordered pairs that matches the input values, always the first, with the output values always the second. Now, why did they mention X and Y before? Okay, for when you're doing your graphing, almost always you'll put the independent, I stuck in an extra word there, your input function on the horizontal axis, the output function on the vertical axis. Okay, it's not function, I'll put values on the vertical axis. So there's graphically, by points on the graph in a coordinate plane, just like I was describing, in which the horizontal axis, I really don't want to call it the x-axis. Everybody does, but it doesn't always have to be x. The horizontal axis represents the input values, the vertical axis represents the output values. And finally, we can do it algebraically. Okay? Now that one on the temperatures and times, that would be a little tough. Okay? You might be able to do it, but that would be one that's more actual data points. Sometimes that's harder to put as an equation. The one with the interest, I is equal to 1,000 R, really easy to write as an algebra. So sometimes this might be preferable, sometimes this. To see it, that would be better verbally, just to state it. That has its purposes too. Make sense? All right. To determine whether a relation is a function or not, you must decide whether each input value is matched with exactly one output value. That's what you've got to show. If it's not a function. If it is, then yes, it is a function. When any input value is matched with 2 or more output values, not a function. Okay? By the way, we're now over on page 36, getting ready for example 1. Okay? Determine whether the relation represents y as a function of x or not. This one is in sentence form, verbally. The input value x is the number of representatives from a state. The output values y is the number of senators from that state. Is that a function or not? Okay, I see a few heads shaking no. Why not? Okay, you said what? 2 same numbers for the input? Okay, with same or different outputs. If they have different outputs, not a function. But if they have the same output, that's fine. Like, let's go back here. Yeah. Oops. Well, this one. If I had listed 1, 9, 2, 13, 3, 15, 4, 15, 5, 16, 6, 10, 2, 13. If I had listed that, I listed 2, 13 twice, so you had 2 2s there, but they had the same output. That's okay. If that next 2 out here would have had a different output, not a function. Okay. So going back to our number of representatives being the input, number of senators being the output, function or not? Say again? It's not or is? I think it is, okay? Now that has a special name, that function. Okay, now Alabama, I can't remember. What do we have? 8 representatives? 6, 7, 8, something like that. No, I live in the 6th district. Some of you know what congressional district you live in? Okay. But I know we have at least 6. I think it's more like 8. Okay, maybe even 9. I don't know. Georgia used to have 10. I think they went up to 11 or 12. Okay. Wyoming, 1. Rhode Island, 1. Okay. So quite a few. Yeah, but so there's different numbers of input. Well, what's the number of output? Senators for each state. 2. Okay. No matter how many inputs you have, no matter how many representatives you have, the output is always 2. So if you have 1, 2. California, maybe 100 or something, you have 2. Okay. So that function would be what we call a constant function. It's always 2. For any input, it's always 2. Any input, always 2. So it can't have more than 1 because all the outputs are 2. Not a 2 and a 7, it can't do that. So that would be a function. Strange function called a constant function. Okay? How about this one? Here's a table. This is numerically. The ordered pairs are in columns here. Is that a function or not? Yay or nay? Second? Yes? Okay, why? Okay.
The inputs, you got 2 that's the same, but the outputs are different.
Are different. Is that allowed? That's a not, because for the same input, you can have 2 outputs. Forbidden. Remember buying the chips in the bookstore. If you bought the same bag of chips and you paid $11 and they paid $10, hey, I want the $10 bag. It's the same. Okay, no. That would not be a function because for the same input, you have different outputs. Now, if these had both been 10s or 11, that would have been fine. You just listed them twice. Okay? And then C, there's graphically a function. Is that, graphically a relation. Is that a function or not? Why not? Say again? Okay, 2 with zeros here, but which is the input, which is the output? The input's the horizontal axis, the output's the vertical. The 0 here is 0 for y. Your inputs are -2, -1, 0, 1, and 2. And none of those have but 1 dot. So for every input, there's only 1 output. See, this one failed because for the same input, different outputs. For every input here, which is in the horizontal, you have 1 and only 1 output. Yes, 2 of these inputs have the same output. That's fine. But any one input can't have 2 outputs. So this is 2. Now, later we're going to have a really nice test for this. It's called the vertical line test. Ever heard of it? Yes. If you can draw a vertical line through any point there, if it hits the second point, not a function. But if it only goes through 1 point, yep, every one of those vertical lines do, that would be a function. Okay? Now that looks kind of like, I think it is, a parabola. More than likely that's a parabola. You don't need to know that yet. But that would be a function. Okay, let's see how they did. First one, the verbal description describes y as a function of x. Regardless of the input value x, the value for y is always 2, called a constant function. Okay? The second one, the table does not describe y as a function of x because the input 2 matched with 2 different y's can't happen. Okay? And the third one, the graph does describe y as a function of x, for every input, there's only 1 dot up there. Wherever it is, yeah, the same dot can be for 2 inputs, but any one input can't have 2 outputs. So yeah, that is a function. Okay? All right. Representing functions by sets of ordered pairs is common in what we call discrete mathematics. That means there's just a fixed number of ordered pairs. It may be 3 million, but there's only a fixed number, okay? That's discrete mathematics. So for any input, you can list the output. Might take you a while. But in algebra, quite often, we have data that come in continuous set. Now, everything we've talked about so far has been discrete, okay? Okay? Not continuous. This would be one that would be continuous. You can give me, okay, which you reckon is the input variable? That's the output. The input is the x, because the function is a squaring thing. You square the x. It gives you the output, y. Okay. Now, I was going to wait to say this later. And remember, x and y don't have to be your two variable names. But when they are, okay, most of the time, remember this. Y is a function of x. Y is a function of x. Y is the output, x is the input. Because here, if I were a cheerleader, I'd say, give me an x. Okay? You give me an x. Give me an x. Any value. Any number. 7. Okay? 7 squared is 49. For any given input, you only have one output. Give me another x. 3. What's the output? 9. How about a negative number? -4. Square it? 16. There's an output. One and only one. Okay? How about 1/2? Can we do fractions? Sure we can. We love our fractions, right? What's 1/2 squared?
1.
You added it. You doubled it. You're squaring it. 1/4. Perfect. One and only one output. So y is a function of x. And guess what? That is not discrete. That's continuous. Any x in the world. Well, I'll say later, and we'll talk about this not too much. When we think of the number line here, think about every little bit of paint on that line. That's a unique number. Okay? Now, discrete would be 1, 2, 3, 4, 5, 6. Okay? Just like our temperatures were. Those are the times of day you measure the temperatures at those times of day. Okay? That's discrete. Okay? Continuous, though, would be any value you want to put in there. Fractions, decimal, rational, irrational, it doesn't matter. Positive, negative, any real number. So when I start doing this, that means all real numbers. That is not discrete, that would be continuous. Okay? So this equation represents, unless we know separately that we're only dealing with integers. If it's integers, it may not be discrete if it's all integers, but if it's integers less than 100, or something like that, then that would be discrete. Okay? So this represents the variable y, the output, as a function of the variable x, the input. Now, we give names for these. I said them earlier. X is called the independent variable. The independent variable, no matter what you name it, that could be time, it could be anything, that's always on the horizontal axis, generally. The output variable, called the dependent variable, because guess what? You give me the x, you can give me any x in the world. It's independent. But once you give it to me, the y is fixed, right? Because you square the x, and that gives me one and only one answer. That then means y depends on x. Depends on what you give me as the x, that'll determine the y value. Okay? Make sense? Okay. Make sure. Yeah. The domain of the function is a set of all the values taken on by the independent variable. In this case, it was x. It doesn't have to be. The range is a set of all the values taken on by the dependent variable y. Now, sometimes x is limited. Okay? For instance, if I'm talking about, say, your age, were any of you ever -3 years old? Yeah. Okay. Your age would always be a positive value. So x doesn't mean any number of the world. It has to fit the problem. Okay? If we're talking about the radius of a circle, can you draw me a circle with a radius of -2? No. Okay? Can't happen. Okay? So that would have to be something greater than 0. Okay? Now, the range can also be limited. Okay? For instance, let's go back here. in this problem, is there any limitation on x, the input? No, that's going to be all real numbers. Positive, negative, rational, irrational, any real number. Okay? Is there any limitation on y? Say again? Yeah, I hear no.
No.
I didn't hear no. No, I mean, okay. How about this? What x could you give me that gave me -3 as y? There's not one. Okay, the question was, what x would give me -3 as a y? There isn't one, because any number in the world, positive, negative, fraction, decimal, whatever, you square it, it's going to turn positive, isn't it? So y would then be everything greater than or equal to 0. X is all real numbers, y greater than or equal to 0. So you see, you can't always, just because it sounds like it can be anything, sometimes it's not. The range of the function, set of all the values taken on by the dependent variable y. Okay. I keep looking here because they skip example 2. And I'm trying to find the right place for it. Yeah. Right here is where we need to do example 2. And since they skip it, we'll do it here. By the way, your book has little blurbs every now and then. There's one on page 37. Really handsome character here. Mathematician's always really handsome, by the way. Many considered Leonard Euler, you pronounce his name like he's from Houston, okay, Swiss mathematician, to be the most prolific and productive mathematician in history. How this guy did it, I don't know. He wrote hundreds of papers, and they were pretty much all of them really groundbreaking. I mean, he was quite a mind, okay? And one of his greatest influences was going to be the stuff of function notation. He came up with the idea, okay? We've been using it ever since, okay? We haven't gotten there yet, but there. Now, why did I mention that? He would be a potential paper topic. Or, how did he develop function notation? Or what are some of the other things he came up with? Does anyone ever heard of the number E? It's a number a lot like pi in that it's an irrational number. You ever heard of E? Okay, we'll get to it later. But let me tell you this. You know why it's named E? Euler. Okay? He came up with that. Okay? Incredible mind. I mean, absolutely incredible. So he's a potential paper topic. Hint, hint, be thinking about your papers. Remember, you're supposed to turn in to me last week your paper topics, weren't you? I didn't get a single one. No, we didn't meet last week. Okay, I'm just kidding. Okay, so anyway, that was a little advertisement there. Let me get my pen set up, and we'll do example 2 here. Now, I think I've mentioned to you before special features that this author has. I've never found another author that had all these. One of these is CalcChat.com, which are the worked out solutions for all the odd number exercises. Every one of them. Okay? CalcView.com is expanded illustrations, tutorials, and stuff on certain of those exercises, the ones that are in red letters. Okay? There is one more thing this guy has, and this is LarsonPrecalculus.com. And by the way, remember example 1 we did just a few minutes ago? At the bottom, right after we've done it, there is a checkpoint. And the audio-video solution for that checkpoint is at LarsonPrecalculus.com. So he has 3 websites out there. They're free. You don't even have to own the book to go to them. If you know they're there, anyone can go to them. But helpful if you have the book, and you can see any of the checkpoints there. But also some of these exercises like this, example 2, see LarsonPrecalculus.com for an interactive version of this type of example. So if what I say and what the book says, and they say, I still don't understand what they're talking about. If they have that there, go to larsonprecalculus.com. He'll interact with you. Okay. Really deep stuff. Okay. So we have that. And I think I told y'all before, I have an ionizing pen here. So everything that's projected, even this ugly stuff I write, is going to be stored on YouTube videos ultimately. So let's do this one. Determine whether each equation represents y as a function of x. So here's the first one, the A one. Okay? X squared plus y is equal to 1. Now, how can we determine if y is a function of x? It's something you've done before, but you probably haven't done it in this context. Okay? Say again? A little louder. Not x, y. You got the right idea, but the wrong variable. Because you want to isolate the y. It's just like you did when you were doing slope-intercept form. Remember? You isolated the y. Got y by itself, saw what happened on the other side. Do the same here. So what would you do? Isolate the y. How would you do that? Subtract x squared from both sides. And what does that give you? That goes to 0. Y is equal to 1 minus x squared. Perfect. And guess what? Now y is a function of x. Give me an x, it produces a y. Any x will produce a y. Okay? You did it. That is a function. And remember what I said earlier? We haven't quite gotten there yet. Remember this, y is f of x, function of x. Okay? How about the B one here? It looks pretty close to the same thing. Minus x plus y squared is equal to 1. Is that y a function of x? Why not? Because the first one was, right? No, okay. Okay, let's try to solve for y again. What would be the first thing you would do? Say again? Add x to both sides. Perfect idea. Okay, these x's go away because they add to 0. This gives you y squared is equal to, I'm going to write it as x plus 1. 1 plus x would be fine either way. That's why I don't like WebAssign. If they wanted 1 plus x, they would go, x plus 1 is wrong. You know, so, not that they would be doing this. But we haven't really solved for y yet. What must we do to solve for y? Square root. Take the square root of both sides. Square root of y squared would be y is equal to, but when you take the square root of both sides, what must you always put? Plus or minus. Remember, negative 3 squared is 9, and 3 squared is 9. So you always wind up with a plus or minus. So it's plus or minus the square root of x plus 1. Right? Okay. Now there are some problems here, but the main one is that a function? Is y a function of x? Give me an x. 3. 3 plus 1 is 4. Square root of 4 is either plus 2 or minus 2. Uh-oh! You gave me 1x. You got 2 y's. Plus 2 and minus 2. Not a function. Okay? Not a function. Okay. Now, so that's how you determine an equation. If it's a function, represents a function, solve for the y. Solve for the dependent variable, whatever the dependent variable is. If it's one and only, function. If it can have 2 or more solutions, not a function. All right, good deal. There is a checkpoint there. You can see larsonprecalculus.com for that as well. Any questions? Okay. Now, sort of the bottom of page 37. When using an equation to represent a function, it is convenient to name the function for easy reference. Now, you can name it anything you want to, but mathematicians are very creative. So, what would we name most functions? How about f? Function f. Boy, really creative, aren't we? Okay. For example, you know that the equation y is equal to 1 minus x squared, that's the one we saw in the A part, right? Describes y as a function of x. What if we give that the name f? You could have named it Fred or Susie. You could have named it anything you wanted to, but they just named it f. So then you can use the following function notation. Thank you, Leonard Euler. He came up with this idea. The input is your x, in this case, because that's what your independent variable is. Your output was the y, but now remember, if there's anything you need to remember in this course, it's this. Y is equal to f of x. If you remember that, you got most of it not. Maybe not everything, but most of it. So instead of naming that y, make it f of x. Some function of x. That's what the output is. So then you can rewrite this as y is f of x is equal to 1 minus x squared. Okay? That's in function notation. So is this much different from equations? No. The only difference is always solve for the dependent variable and then name it f of x. Or g of x or g of t or whatever you want to name it. But that's going to be it. The input variable goes inside the function notation. The dependent variable is what that function notation represents. Okay? Make sense? All right. Now, that symbol f of x is read, the value of f at x, or simply f of x. Okay? We just get so used to saying it, it's f of x. The symbol f of x corresponds to the y value, like I just said. For any given x, that's the y that corresponds to that x. So put in one x, you get one y. Put in another x, you may get one different y, but you're going to get a y. So you could write, and this is, to me, the most important thing to remember in this course. Y is equal to f of x. Or dependent variable is equal function of the independent variable. That's really the best way to say it. Keep in mind that f is the name of the function. Fred, or whatever, okay. Whereas f of x, the f is the name of it, f of x is the value of the function at that value x. So here's a function, a different one. F of x is equal to 3 minus 2x. Okay? Now, if I said, what is f of negative 1? What would you do? Given that function. Can you do that? Yes. Instead of x, because x, negative 1 takes the place of x, you put negative 1 in place of x here. So what would that give you? 3 minus 2 times negative 1. What's negative 2 times negative 1? Plus 2. 3 plus 2 is 5. There you have your f of negative 1 would be 5. You put a number in for the x, you get a number out for the y, or f of x. How about 0? Can you do that? Can you put nothing in there? Sure. What would that give you? Which is? 3. Yeah, I love 0 to plug in. That's my favorite. Okay? Most of the time. Okay? How about 2? Can you put a positive number in there? What would that give you? Negative. Okay, 3 minus 4. Negative 1. All right, yeah. So your f of x, of 2 would be negative 1. Now notice your f of 1 was 5, f of 0 was 3, and f of 2 was negative 1. That's what we call a decreasing function. Okay? We knew that, didn't we? If this had been a y here, what would this represent? Say again? An equation. And what would this part over here represent? minus 2x plus 3. What does that sound like? Say again? Algebra, yeah, for sure. Think graphing. We love to graph, don't we? By the way, if you haven't recognized this, you're going to. This butt loves to graph. We're going to be graphing just about everything, okay? What would that represent? Negative 2x plus 3. I've already used the term once today, at least. Negative 2 would be the 3 would be slope, intercept form. Negative 2 is the slope, meaning it's going downhill, right? And intercept 3 when x equals 0, y is equal to 3. That's where it intercepts the y-axis. Y-axis is 3. We already determined that. Okay? So yeah, that also represents the slope-intercept form of a straight line. Okay? And that's why it was decreasing. That was way more than the problem was asking for. All right, so here's what they did. For x equals negative 1, plug in the negative 1 where you saw the x. You plug it in here and you plug it in there. Then you do the math. 3 minus 2 times minus 1. Remember rule of order of operations, multiplication before addition, subtraction. So that would be 3 plus 2, 5. Perfect. 0 in there, as you said already, that's 3. By the way, that's your y-intercept. Okay? And here, alpha of 2 would be 3 minus 4. That took you a while. That was minus 1. Make sense? Okay. Although f is often used as a convenient function name, just like if I say, what variable you want to use? What are you going to say most of the time? X. That's everybody's favorite variable. Well, f is everybody's favorite function name. But guess what? The variable could be y, it could be t, it could be m, it could be just about anything. Well, similarly, you can use your function to be something else. It could be g, it could be r, it could be a variety of things. Okay? Although f is often used as a convenient function name, x is often used as the independent variable, you can use other letters. So f of x equal x squared plus 4x plus 7. What would f of t be? T squared minus 4t plus 7. Okay? What would g of s be? Yes, s squared minus 4s plus 7. Yeah. You can name them anything you want to. They all define the same function. Okay? In fact, even though you think x is the independent variable, it's the one that stands alone, actually it's just a dummy. It's a placeholder. Because the important thing is, what is the output? Okay? You could put a stickman in here. Alpha stickman would be stickman squared minus 4 stickman plus 7. You can do anything you want to. They're going to use a box, a rectangle, anything. It doesn't matter. You don't even have to have a variable name. Just understand that's standing for whatever you put in there. Okay? So here they use the rectangle. Alpha of rectangle is equal to rectangle squared minus 4 rectangles plus 7. Give me a rectangle, I'll plug it in, you get the same results, right? Okay. A function defined by 2 or more equations. Oh, this should be on a different slide. This is the one that's really bizarre. But they just said, oh, we got room, let's put it here. This is hitting a new topic here. Okay? So before we go to the new topic, let's do example 3. Since they skipped it, let's do 3. We'll come back to piecewise defined function. See, do we? No. Okay. Let's do example 3. Let g of x equal to minus x squared plus 4x plus 1. Is that the same one we were using before? No, that was never mind. Okay. First part says, what is g of 2? You tell me. What would you do? Minus 2 squared plus, say again, 4 times, you can make fun of my writing. I understand. It hurts, but I can live with it. Okay. 2 plus 1. Okay, here, folks, we have a first little test of, you remember your please excuse my dear Aunt Sally. I don't know what she did, but please excuse her, okay? Now, how would you do that? Especially that first term. Tell me what the value of the first term is. Okay. Not quite. Because remember, please excuse, you do exponents before you do addition, subtraction, which is changes the sign thing. So it's minus 2 squared, minus x squared. You square the 2 first, that's 4, and then you negate it. So it's a negative 4. Okay? Now, if that was in parentheses, then you square the whole thing. That would have been a plus 4. Negative 2 squared would be 4. But minus 2 squared is 4, minus that would be negative 4. So this will be a negative 4. Help me. Plus 8 plus 1, and that's equal to 5. Perfect. Very good. Okay? Make sure the book got it right. They did. Now, the second one says, what is g of t? What would that be? Negative t squared plus 4t plus 1. Perfect. So easy. Okay? But how about this one? What is g of x plus 2? What? What would you do with that? Okay, you put a negative, and then you put x plus 2, if I could write, squared, because your thing was squared, plus 4 times x plus 2 plus 1. Yes, you got it. But now we got some work to do, don't we? So let's do the work. That'd be a minus. Now we got to square that binomial. Do any of you know how to do that kind of in your heads? Or how do you do that? You tell me. Square the first one. Okay, I like that. That would be x squared. Next. Okay, I heard a plus 4, and that certainly is there. But you left out the middle term. Okay, so if you don't know how to do it just looking at it, what does x plus 2 squared mean anyway? What does squaring something do? Multiply it by itself, doesn't it? So come off to the side and do x plus 2 times x plus 2. And now how would you do that? FOIL it. Okay? First is x squared. That's what you got before. Next is plus 2x. That's the outer. Plus 2x is the inner. And plus 4 is the last. Okay? Okay? And then you combine like terms, and what do you get? X squared plus 4x plus 4. You left out the middle term. 4x. Okay? And besides that, you get a smiley face, right? And you're happy you got it right. All right, good. Okay. Now, if you don't want to go through that every time, here's how you square a binomial. Square the first term. You're absolutely right. Then it's twice the product of the two terms because they're identical. So 2x doubled is 4x, and then square the last. So that's how you can do it, just writing it down. But if there's any doubt, go back and forth. Okay? Next. plus 4x plus 8 plus 1. Okay? Now the next thing you got to do is negate those things in parentheses. Okay? What would that be? Help me. Negative x squared minus 4x minus 4 plus 4x plus 8 plus 1. Now what? Combine like terms. There's no other square term, so that's minus x squared. How about your linear terms? Yeah, minus 4x plus 4x adds to 0. Okay? And then add the constant terms, and what do you get? Second? Plus 5. There you have it. There's what g of x plus 2. Not very obvious. Okay? It doesn't look at all like it, but there's your g of x plus 2. Minus x squared plus 5. Okay? Good deal. Any questions on that? Make sure the book got it right. Oh, look at them. They got it right too. Good for them. Okay. There is a checkpoint here, and since it felt like I was a little bit of a dentist pulling teeth up here, might not be a bad idea to do your checkpoint. And here's a hint for you. I've had students complain about the class before, and here's the best thing I can come up with. As soon as you get out of class and you don't have another class coming up, as soon as you can do so, go back and do the checkpoints. Because while it's sort of fresh on your mind, go do those checkpoints. Because just like the examples we just did, that reinforces them. And then when you have more time later, do your homework exercises. But as soon as you can, especially if this is sort of new to you, do those. A good thing to do. And if you have problems, go to larsonprecalculus.com and he can clue you in on that. Okay? Now, let's go back to this sentence here. A function defined by two or more equations over a specified domain is called a piecewise defined function. Blah, blah, blah. What in the world is that talking about? Well, here's an example. This is example 4. Evaluate this function f at x equal negative 1, 0, and 1. Okay? Now this is a piecewise defined function. If f of x is this thing for any x is less than 0, it's this thing for any x is 0 and beyond. So it's good for all real numbers, but it's just different definitions there, right? Okay. So let's do f of x. Let's do a f of negative 1. Okay. Now the first thing you got to do, I sort of do it stupidly here. First thing I say do is say, where are you, Waldo? Okay? Where is x equal negative 1? Is that here or is it here? It's which? Top or bottom? Top. So therefore we use this definition. Don't use this one. Use that. So what would you have? F of x would be, f of negative 1 would be negative 1 squared plus 1. And what's that? What's negative 1 squared? 1 plus 1. 2. Didn't know you'd be doing such high-level math today when you came in, did you? 1 plus 1 is 2. Okay, we got it. All right? Okay. There's f of negative 1. Okay? Next they ask for, what is f of 0? And what's the first question you ask yourself? Where are you, Waldo? And where are you? X equals 0. Top or bottom? Bottom, because this is for x is less than 0. 0 is not less than 0. 0 is equal to 0. That's what that line under there means. So you use the bottom. And what does that give you? Help me? 0 minus 1 is equal to negative 1. Done. Excellent. Way to go. Okay, how about f of 1? What do you ask yourself? Okay, where are you? You're again greater than or equal to 0, so therefore you use the bottom one. You use 1 minus 1 equals 0. You already did it. Way to go. Any questions on that? Does everybody see it? Always figure out where you are, which piece of this. A piecewise defined function can be a whole bunch of things. Now, is this just something mathematicians have made up to make it more difficult and confusing? No, it isn't. You use piecewise functions all the time. You ever been to the post office and you mailed a big fat letter? What did you have to do first? Weigh it, because different weights of letters require different postage. Piecewise defined function is, what is it now, 48 or something cents for the first ounce, and then it's 82, whatever it is for the next. And yeah, that's a piecewise defined function. Okay? So yeah, you use these things. I bet you some of you cell phone plans used to be that way. If you use fewer than so many minutes, you pay this much, and if you use so much data, you pay this much. If you use piecewise functions all the time, right? We love them, don't we? Yes. Okay. Let's see what they did. I'm going to erase this so we can write, and let's see what. Oh yes, because x equals -1 is less than 0. You use the top one, so f of x will be x squared plus 1, plug in the minus 1 squared plus 1 will be 1 plus 1 is 2. Good for them. Okay? And then for 0, that's in the second equation. You use f of x equal x minus 1, so 0 minus 1 is -1. Very good. And then for the third one, x equal 1, again, use the bottom one because 1 is greater than 0. Use f of x is 1 minus 1, which is 0. Nothing. Zilch. All right. And again, there's a checkpoint at the bottom. Good idea to do those. As soon as you can get a break, sit down, get your checkpoints done. Okay. Want to see if we can. No, let's see. All right. I have a feeling we're not going to have time to do example 5. Sorry about that, team. I know y'all wanted to do that, but we'll have to wait. We'll do that on Thursday. So we'll start with example. But don't close the books yet, because I want to give you some homework exercises. Yes, okay. Do either 5 or 7 or both. In fact, I would do both of them. One is sort of a mapping type one, and one is sort of a table type one. Number 7, by the way, has a red 7 there. That means calcview.com. Both of the odds would be calcchat.com. Do number 9. Do any of the odds 11 through 17. Now 11's on calccheck.com, and 17 and the rest of them are the odds are on CalcView. And as I pointed out before, if you have the reader on your phone, you can go to the symbol here, read that, and it will probably take you to some help if you need it. Okay? Then do any of the odds 19 through 29. Now all those odds are on calcchat.com, 21's on calcview.com. Okay, then do either 31 or 33, and both of those are on calcchat.com. Stop there, we'll pick up the rest of those next time. Anyone need those again? All right, and I got our first paper in. Yay, way to go. Okay. Be working on your papers, folks. All right.